Introducing the concept of mechanical energy will require us to engage in a bit of creative accounting with the work energy theorem, EWOC here. But of course, it'll turn out to be quite useful. So this video is structured as a how to conduct an energy audit of a scenario, in particular in this first part, a scenario with a single moving object. So by energy audit, I mean what we're going to do is identify all the forms of energy present in the scenario, group those into categories, and then track how energy is transferred from one category to another as the object moves around. So in this example scenario, I've got a block sliding on a rough surface with a linear spring here, an elastic spring. So, question one to ask yourself, what interactions, meaning forces, is the object experiencing? So you would look at this scenario and say that, well, there will be a normal force, a force of gravity on the block, a force of kinetic friction as it slides around, up the ramp, down the ramp, and a spring force whenever it's in contact with the spring over here. Two, ask yourself, of those interactions, which ones are conservative and which ones are non-conservative? Here is where we begin our grouping of these forces into categories. So you'd look here and say that of those, we know, of course, that gravity and an elastic force are conservative forces, and pretty much anything else that we've discussed so far is not. So that normal force and that force of kinetic friction, non-conservative. So regarding this grouping of the forces into these two categories, I want to make an important note here. For energy purposes, the difference between internal forces and external forces is just not very important. These are distinctions that we make when we're discussing the momentum of a system. Here's like our summary of momentum equations, momentum results for objects and for systems. And we see here in the impulse momentum theorem for a system, and in Newton's second law for a system, it's all about identifying the external forces as opposed to the internal forces. They are the ones, the external ones, that can change the momentum of a system. So that's critical for a study of momentum, but if you're looking at the energy of a system, internal versus external, not very important. It's conservative versus non-conservative that plays the key role in energy transfers. So step 3 then. Now that we've identified our conservative and non-conservative forces, we're going to take the work energy theorem and kind of shuffle some terms around to define what we'll call the mechanical energy of our system. So starting with the work energy theorem here, left-hand side we'll write out the sum of all the works, one term for each force that's present. Each force that's present could be doing work. So 2 works done by non-conservative forces, 2 works done by conservative forces, and for those 2 works done by the conservative forces, we know that a conservative force is defined as one that can be related to a corresponding potential energy. So each work done by a conservative force is equivalent to the opposite of the change in the corresponding potential energy. So I'm going to replace each of these works by conservative forces with the opposite of the change in the corresponding potential energy. Work done by gravity is equal to the opposite of the change in gravitational potential energy, and the work done by the spring is equal to the opposite of the change in the spring potential energy. So now I'm going to regroup these terms. I'm going to move the delta U's over to the side with kinetic energy. So I've got these non-conservative works here and the kinetic and potential energies, or the changes in those energies, over here. Now I'll just flip the 2 sides, put our kinetic and potential energy changes over here, and define this sum of changes as the change in the capital E mechanical energy of the system, showing that the change in this mechanical energy is due entirely to works done by non-conservative forces. So We will, in general, define mechanical energy of a system as the sum of the kinetic energies of the moving objects in the system plus any potential energies in the system. So there we have it, the mechanical energy of our mass plus earth plus spring system. Recall that a potential energy always requires an interaction between objects. So UG is the interaction between the mass and the earth. US is the interaction between the mass and the spring. So we do have to think in system terms, the mass, earth, spring system, if we're going to be including potential energies. That said, even though we're talking about systems, the internal versus external distinction is not important to us here. It's the conservative versus non-conservative distinction that matters for energy. And then on our right-hand side, we have what we'll call the net work done by all non-conservative forces on the system. So here's our general statement of conservation of energy. The change in the mechanical energy of the system is due exclusively to the work done by non-conservative forces on the system. The principle at work here is that conservative forces will transfer kinetic energy into potential energy and vice versa in such a way that they keep the total mechanical energy constant. So we know that they act in a way to attempt to minimize the potential energy, and as they're doing that, the total energy E here is kept constant. So our conservative forces will sort of transfer energy from this category into that category and back again without losing or creating any energy in the process. Only these non-conservative forces over here change the mechanical energy of a system. So the sibling principle is that non-conservative forces, they add or remove mechanical energy to or from the system. Often they do so by converting mechanical energy into one of the several forms of non-mechanical energy, such as thermal energy, or heat, acoustic energy, meaning sound, chemical potential energy, electrical energy. Non-conservative forces will change mechanical energy into these and vice versa. Okay, so that was kind of a bit of a discussion that started with us shuffling the terms here to define mechanical energy as the sum of the kinetic energies of the moving objects and the potential energies in the system, which led us to this statement. This becomes our conservation of energy equation to work with. Now, the next step, once you've got this, is to ask yourself, what two moments in time do I want to compare? Meaning, do I want to compare when the object is at the top of the ramp to when it touches the spring, or when it's from the bottom of the ramp to when the spring is fully compressed, or maybe from the moment when it starts with a fully compressed spring to the moment it reaches its highest point up here? Energy is useful for comparing two different moments in time in between which the object has moved around and energies have shifted somewhat. Contrast that with Newton's second law for an object or for a system, which is all about finding the acceleration at one moment in time. This is the instantaneous net force and the instantaneous acceleration. Newton's second law is all about freezing time and analyzing the acceleration at that one moment. The usefulness of energy is that we can compare two different moments in time. So pick your two moments and then consider the time interval between those two moments. So ask yourself, during that time interval between the two moments you chose, are any of the non-conservative forces actually doing work? So in our case, we do have some non-conservative forces that are present. They are there, but you have to ask yourself, are they actually doing work between the two moments you chose? If the answer is no, if none of the non-conservative forces are doing any work, that means the net work done by non-conservative forces is zero, so the change in mechanical energy is zero, And we would say the mechanical energy at your moment 1 equals the mechanical energy at your moment 2, and the mechanical energy of the system is being conserved from moment 1 to moment 2. But if, yes, there are some non-conservative forces doing work between your two moments, then we have a non-zero value here on the right-hand side. The work done by those non-conservative forces is going to be adding or removing mechanical energy from your system. So we have to write the equation like this. Delta E becomes the mechanical energy at the final moment minus the mechanical energy at the initial moment is equal to the net work done by non-conservative forces between those two moments. So the mechanical energy is not conserved in this instance. So for our example, we've got potentially work done by that force of kinetic friction and work done by our normal force. Those are our two non-conservative forces on that block. So we would write our conservation of energy equation like this. The change in mechanical energy equals the sum of those two works. And think for a moment. Let's say that our moment 1 and moment 2 are, let's say we'll release the block from rest up here and let it slide down, come in contact with the spring, and compress the spring until the spring is fully compressed and the block comes to rest for a moment before being shot back out. So moment 1, released from rest. Moment 2, fully compressed down here. Between those two moments, are these non-conservative forces actually doing work? Is friction going to be doing work? Yes, of course. It'll be slowing the block down. What about that normal force? What's the answer? Is it doing work? Is it? Is it? Correct. The normal force is not doing any work because, what's the reason? That's right. That normal force is perpendicular to the velocity at all times as the block slides along this surface. Since the normal force is always perpendicular to the surface, and the velocity is always parallel to the surface. So being a right angle between those, normal force does not do any work. But that kinetic friction is going to be doing work. So our equation would be this. So the mechanical energy at moment 2 minus the mechanical energy at moment 1 is equal to the net work done by the non-conservative forces. In this case, the work done by kinetic friction, which we expect to be negative. The force of friction will be always pointing opposite the velocity, doing negative work, removing mechanical energy from the system. Friction reducing the mechanical energy of the system. Friction, in fact, converting that mechanical energy into primarily heat, but maybe some sound as well, if you hear the box make a scraping sound as it slides across that surface. So we're losing mechanical energy as friction converts it into these forms of non-mechanical energy. Okay, your last thing to ask yourself here as you're setting up an equation to solve in your energy audit here. This is the equation that we've been working towards building. Now you have to ask yourself, at these two moments, moment 2 and moment 1, are any of these energies zero? Do any of these vanish? What forms of energy are actually present at those two moments? That's the last step. So at a given moment, ask yourself, does the object or system actually have each of these forms of energy? Does it have kinetic energy at that moment? Well, simply ask yourself, is it moving? Is the object moving at that moment? Are any of the objects moving? If they are, then yes, there's kinetic energy. Does the system actually have gravitational potential energy at that moment? Well, ask yourself, is the object above or below your y equals 0 reference point? Oh, reminding us that we were supposed to choose a vertical reference point. You have to decide where y equals 0 is. You know that the choice of reference point doesn't matter, but you do have to choose one and stick with it. Keep that reference point fixed and then check at the moment of interest, is your object actually at, above, or below your y equals 0 reference point? Then ask yourself, does the system actually have elastic potential energy, spring potential energy? So you look at your spring and think, okay, at this moment, is the spring at all stretched or compressed? If it is, if it's either stretched or compressed, if the spring is not at its natural length, then yes, it is storing energy in the form of elastic potential energy. So in our particular example here, if this is moment 1, released from rest, this is moment 2, max compression down here as the block slid this way, and I've selected my vertical reference point. I'm going to say y equals 0 here at the low point. Then, looking at this equation, we can identify that at moment 2, block is at max compression. It's momentarily at rest, therefore it's not moving, so no kinetic energy at moment 2. It was released from rest up here, so wasn't moving initially, so no kinetic energy at moment 1. Gravitational potential energy. Here at moment 2, the block is at our vertical reference point. It's at y equals 0, so no gravitational potential energy. At moment 1, it is above the vertical reference point, so yes, we do have gravitational potential energy at moment 1. Spring potential energy. At moment 2, the spring is compressed. Compressed spring is storing energy, but at moment 1, the block is up here, the spring is down here. The spring would be just sitting at its natural length, uncompressed, so no spring potential energy. Spring is not storing energy at moment 1 when the block's not touching it. So then these would be our terms. We would just have 1/2 k x2 squared, x2 meaning the compression of the spring at moment 2. And then our gravitational potential energy here, mgy1, y1 being the height of the block above the reference point at moment 1. And the right-hand side, of course, would be the work done by kinetic friction between those two moments, which we're expecting to be negative, since that friction would do negative work, reducing the energy of the system, converting mechanical energy into heat and sound as the block slides along. So if you had information about the UG and the US, you could use this equation to solve for the work done by friction, or potentially, if you had enough information about the path and about friction here, you might have to integrate to compute this work integral to find the work done by kinetic friction, which again we're expecting to be a negative value, and then use that to solve for one of these two terms here. The point is, we have constructed our full conservation of energy equation here and completed our energy audit.